just from here to here. Okay, just from here there to there. Okay, so the answer, so the when you do that, the answer will be no, sorry, not this way. I do apologize. Remember we had an analysis that the analysis start from where? Ymax. You all remember that, right? We say that we can also apply the analysis that our analysis start from Ymax. Okay, you can also use this when you use the Ymax analysis. There is no positive or negative first moment of area. Okay, so when that's the case, the area to consider is this area now. Okay, so by doing that, okay, what will happen? So now I'm going to use this to find our QZ at point C, right? So the width now is what? The width is, so 10 plus 1 plus 1, the width is 12. The depth is 2, the y bar is 25. Okay, so 12 times 2 times 25 is equal to 600 millimeter cube, or 600 times 10 to the power minus 9 meter cube, right? So we know at point C over here, we only have it as a white what? White flange, because you only have Q in one side only, right? So when that's the case, you can have the shear stress at point C is equal to 5,000 multiplied by 600 times by 10 to the power minus 9 divide by 133.76 times 10 to the power minus 9 divide by 2 times by 10 to the power minus 3. So this will be equal to 5,000. That's a 600 pound, 5,000. That's a 600 pound minus 9 divided by 133.76 pound minus 9 divided by 2 power of minus 3 is equal to 11.214 times 10 to the power 6 Pascal. Both ways, the answer will be the what? Will be the same. Okay, so you decide which you prefer. Okay, as I said, the answer will be the same. Okay. Personally, if you ask me which is my preferred way, I think I prefer to use this method over here. Okay, because it makes you look at the rules of where the terminal is from, right? It makes you look at the direction of the shear flow. Whereas this is all just what? Math. The analysis starts from Ymax. Okay. Next, we want to look at point D. Okay. So point D is very straightforward, and point E is very straightforward. It has to start from the what? The terminal one, right? So if we look at point D, let me copy this whole information because this information is important to me. Okay, so let's look at point D. Okay, so if we look at point D, right, looking at the direction of the shear flow, we know that it's going to be from terminal 1, and it's going to be box beam. And we know we're going to use it as 2Q, right? So you have Q at point B, which is equal to, again, we have the what? 20 times 2 times by 25 plus by the left and right 2. So this is the web now. So 2 up to the geometric center is 26 multiplied by 26 divided by 2, right? So this will be equal to 20 times 2 times by 25,000 plus by 2 times 2 times 26 times 26 divided by 2 is equal to 1352. So 1,000 plus by 1352 is equal to 2352. Okay, so 2352 millimeter cube, or you can have it as 2352 times 10 to the power minus 9 meter cube, right? So the shear stress at point D, so we know that this is equal to 5,000 divided by 133.76 times 10 to the power minus 9. First moment of it is 2352 times 10 to the power minus 9. Box beam thickness, right? So this is equal to 5,000 power minus 9 divided by 133.76 power minus 9 divided by 2 divided by 2 power minus 3 is equal to 21.80, right? Times 10 to the power 6 Pascal. And finally, for point E, right? You know that it's from terminal 1 and it's box beam to Q, right? So Q at point E will be equal to 2 times 20 times by 2 times by 25, which is equal to 1,000 millimeter cube, or 1,000 times by 10 to the power minus 9 meter cube. And then we have at point E, so this is equal to 5,000 multiplied by 1,000 times 10 to the power minus 9, 133.76, left and right thickness, right? Because 2Q over here, that's why you have to divide by 2 over there. So 5,000 plus 1,000 power minus 9 divided by 50.76 power minus 9 divided by 2 divided by 2 power minus 3 is equal to 934. Is equal to 934 point, wait, let me do it. 5,000, 1,000 power minus 9 divided by 133.76 power minus 9 divided by 2 divided by 2 power minus 3. 9.345 times 10 to the power 6 Pascal. Okay. So as I say, one of the most difficult or complex structure, okay, and it's not difficult because there are two rules that we apply, okay. The rules that, or there are two criteria that we focus on, okay. We focus on where the terminal, okay, and direction of shear flow, okay. So if you were to ask me about a revision, I think this is a very good revision to see whether you really understand the concept well. Okay, as I said, this is one of the most difficult problems. Okay. Next, I'm going to any questions so far? Anyone? Okay. Again, you cannot just watch my technique and just say, okay, I think I understand. Okay. You have to go to the homework and apply what I teach. Okay. Then you will gain confidence. Okay. Don't wait for the last moment to do your homework. Do your homework early. Okay. Then you got time to figure out. As I say, for me to solve problem like this, I practice a lot. Okay. I've been teaching this course for 16 times. I've been practicing a lot. That's why I have the confidence. And I want you all to have that level of confidence also. Okay. The next problem that I want to do, okay, I think the diagram is last week's. I have it. Okay, it's probably from your homework. It's probably from your homework. So if I can find, yeah, I found it. So is this problem over here. And I'm going to change the question, right? because some of you ask me how am I going to study from the final. Okay, so by now you should know how I ask you question. Okay, I combine the homework question. It's actually one question, but I combine two different question into one question, as you all know by now. Okay, or I will change the direction. Okay, like for this case. Okay. Okay. Right. Knowing that the vertical shear V cause a maximum shear stress of 75 megapascal in an extruded beam. Okay. Uh, having the cross section shown, determine the shearing stress at the 3 points indicated: A, B, and C. Okay. So the thing about this question is we are given that tau max, right? We are given that tau max is equal to 75 times 10 to the power 6 Pascal. Okay. Now, it's helping us in the sense that we have to find or analyze where tau max occur. And it's asking us, is it at point A, point B, and point C? Okay. Right? You can see it's asking us, A, point A, B, or C. Right? And the thing now is this, okay? Why point A, why point B, and why point C, and not elsewhere? Okay. So if we were to analyze, okay, so we are going to look at points A, B, C. And if we were to look at T, okay, before we look at T, right, we are going to have this as our Vy, right? And this structure, half of it or part of it is thin wall and part of it is non-thin wall. Okay, let me elaborate. Okay, so you design the shear flow. So we have a terminal T1, T2, T3, T4. Now, at the center part over here, right, the shear flow will flow down this way. So what I'm trying to highlight is this. This structure is very interesting. From here to here, based on the shear flow that we have designed, this is non-thin wall. Now, based on here, this is what? Thin wall. Right? It's a combination of both. In this context, why this is important? Because it will determine what thickness you're going to use. Okay, it's going to determine what thickness you're going to use. So at point C, right, the thickness is 10 millimeters. At point B, the thickness is 20 millimeters. Right? At point A, it is 120 millimeters. Okay. In terms of Q, right? At point C, is Q mean. At point A is our Q max. At point B is neither Q max or mean. Okay, is just a certain value Q. Okay. So the question now lies to us. Okay, before I go there, why they pick point A, point B, and point C? Because at point A, right, you have what? Q max. At point C,